Yesterday we learned a postulate for similar triangles, and that was called the angle-angle similarity postulate. It said if in two triangles we know that the angles match up, then that means those triangles will have to be similar. Today we're going to have two theorems about similar triangles, and their names are probably going to be familiar because we've seen them before a couple times. So today we're going to talk about side-angle-side and side-side-side similarities. We talked quite a while ago about side-angle-side and side-side-side congruences, which said if those things were matching up perfectly, then the triangles would match up perfectly and be congruent. Then we had inequality theorems, which said for side-angle-side, if the two sides match up but the angles don't, then it's kind of like a hinge. And opening or closing that hinge will change the size of that third side of the triangle. And likewise with side-side-side. Today with similarity, side-angle-side says that if we have two triangles and we know in those triangles that one angle is congruent and that some sides around that angle are in proportion, then the two triangles will be similar, which means that the other two angles must be congruent and the other set of sides must also be in proportion, even though we weren't given information about them. If we know one angle is congruent in them and the sides that surround that angle, and it has to be those sides, it can't be other sides, it has to be the sides that are surrounding that angle, are in proportion, then those two triangles will be similar. Side-side-side similarity says that if I have two triangles and I know all three sides are in proportion, then I know those two triangles are congruent, which means, or rather similar, which means the angles must be congruent. Okay, even though we don't know anything about the angles. If we know all of the sets of sides are in proportion, then that means the triangles are similar, which means the angles are congruent, even though we weren't given anything about the angles. Okay, so now we have three different ways that we can say two triangles are similar to each other. We can do angle-angle similarity from yesterday, or we can do side-angle-side similarity, or side-side-side similarity. So we have three options. So we're going to look at some examples of finding similar triangles and determining whether or not they are in fact similar. So for our first example, we're going to have two triangles. Not drawn to scale. And we want to determine if these two triangles are similar. If they are similar, we want to name them, and remember the order of the letters matters. Now, one of the things that's going to happen in your pictures is the triangles aren't going to necessarily be drawn in the same orientation. So that means we can't think about comparing left to left, right to right, bottom to bottom, because they're not necessarily turned and flipped in the right directions. So what we want to do is think about comparing small to small, medium to medium, and big to big. That should work out no matter how the triangles are turned or flipped. So first, if this works, given this information, which one of our theorems or postulates would we be applying? Side-side-side, because that's what we know everything about. So we would be applying a side-side-side similarity if this actually works out. So now we want to see, does it work out? So what we're going to do is compare small to small, medium to medium, large to large. So the small in the first is 10, and the second is 16. The medium in the first is 15. The medium in the second is 24. The big in the first is 20, and the big in the second is 32. And what we need to see is, are these all actually the same ratio? Because if so, that should be the scale factor between them. If we have some different ratios going on, then side-side-side similarity doesn't work, and these actually aren't similar. So 10 to 16, does that reduce?
Yeah.
By 2 to give 5/8. 15 over 24, what does that reduce by?
3. 3.
3 to give 5 to 8. 20 to 32, does that reduce? By 4 to give 5 to 8. So it works out and we have a scale factor of 5 to 8. Yes.
How does that work? Because the FHG triangle looks, it has
Well, remember, it's not drawn to scale. So don't trust my drawings at all. The book, maybe you can eyeball a little bit more, but still not even. Don't say that it looks like it or doesn't look like it.
Yeah,
I'm going to set up the proportions. So I'm going to name my first triangle FGH. Now, when we name the second triangle, we have to be careful about the order of the letters because the order of the letters means something. So F, as an angle, is the angle that is between the small side and the big side. So we need to match that in the second triangle with the angle that is between the small side and the big side. Which letter would that be?
X.
X is between the small and the big. So that means X must come first in that second name. G is between the big side and the medium side. So I need to then find the letter in the second one that's between big and medium, which is S. And then by process of elimination, the last one must be R. Okay. H is between small and medium, and R is between small and medium. Okay, so name your first triangle whatever you want, but then when you name the second one, you need to look at where is that angle and what sides is it between, and make sure you're picking the same sides for the other one. Okay, if these two would be similar, which postulate or theorem would we apply here? So we've had 3 different ways, what we learned yesterday and what we learned today. 3 different ways that we can say we have some similarities. So which one would apply here? Angle, angle. Okay, so that's what we'd be going for, is looking to see if the angles match up. Now we only know some of the angles. For angle, angle, we need 2 sets of angles to be congruent. So we definitely have at least one, 70 and 70, and then we need to decide are the other ones. Well, 60 and 40 aren't, but maybe those other angles still work out okay. How do we find out what those other angles are?
You add up the 2 angles that you know and subtract that from 180.
Okay, so a triangle should have 180, so we can add up what we've used up so far and subtract that out to see what's left. And that angle would have to be 70. And then the other one, we add up to 150, so that angle would have to be 30? No. That adds up to 130, subtracts out to 50. So no, all the angles don't match up. So these 2 triangles are not similar. Okay, the angles don't match up. If the angles did match up, we could apply an angle-angle similarity, but they do not match up, so it doesn't work. And that's nice because it's a lot less work. We don't have to name anything if they're not similar. For our next example, if these work, which similarity method would we be applying?
Side angle side.
Side angle side. If it works, it would be a side angle side similarity. How? I only know stuff about sides.
Because of the vertical angle.
Vertical angles. Okay? So if this works, we have a side angle side similarity. So now we need to determine if it does work. We know we have a congruent angle. Then we have to check to see if the sides are in proportion. And remember, we can't think about top to top and bottom to bottom or left to right, because those things are going to all be possibly moved and turned around. So what we need to think about is smalls to bigs. So in the first one, the small side is 8, and in the second one, the small side is 6. In the first one, 12 is the bigger number we're given, and in the second one, 9 is the bigger number that we're given. So then we need to set these up. 4 to 3. 4 to 3. They reduce to the same thing. So these two triangles are in fact similar. Now we need to name them. I can name the first one whatever I want. For the second one, R is next to the unknown and the bigger. So in the second triangle, which one is next to the unknown and the bigger? U. S is the angle that we know in both of them to be congruent, so S has to match with S, which by process of elimination means T has to be the other one. Okay. Questions on how to match up those letters? For me, that's the hardest part. It's trying to figure out the names. Okay, for the next one. We're given a lot of the same stuff here. Actually, really the exact same numbers even. Just put him in some different locations. So we still know some vertical angles. So can we apply side angle, side similarity to this?
Yeah.
I think so. There's 2 sides and 2 angles.
There are 2 sides and an angle in each triangle. Is it side angle, side?
No.
Which angle would we need to know if this is going to work out?
Z and
W and Z would have to be the angles that we know about, because for side angle side, we need the angle to be between the sides that we know about. So we don't know the right angles for this to work out. So these might be similar, but they might not. There's not enough information here, so we're going to have to say no conclusion. We can't apply any of the theorems we know. Okay? For side angle side, it must be the angle that's between the sides. Yes.
Will we get marked down if we say not similar instead of no conclusion, or no conclusion instead of not similar?
No, I probably won't be that picky about that. For our next one,
I like your infinity scarf.
thanks.
That's true.
Oh, yeah,
The freshman and junior.
Yeah, they don't have English.
Freshman problems.
All right.
Another advanced math class.
Sorry, freshman.
If we apply one of our theorems, which one would we apply? Side angle side. In both of the triangles, we know 2 sides. We know the angle between them is a right angle. So side angle side is what we have here. Now we need to see, does it actually work out with the numbers that we have? So in the left-hand triangle, what is the small side? 15. In the right-hand triangle, what is the small side? 9. In the left hand, what is the big side? In the right hand, what is the big side? 15. 15's in both of them, but it's the small side in one and the bigger side in the other one. Okay. Like X.
Yeah, I thought it was an X.
I could understand thinking it was like a K, but it doesn't at all look like an X.
Yeah, that's fine.
No.
No, the other one. 2 at 2.
That still doesn't look like an X.
Now
So that 15 is in both of them. So, but in one of them it's the small and in one of them it's the big. Do these reduce to the same thing?
Yeah.
What do they reduce to? They both reduce to 5/3. So we do have a scale factor. These 2 triangles are in fact similar. So now we need to name them. I can name the left one whatever I want. I'm going to call it PLN.
That was a C.
Oh my goodness.
It looks like a C.
Yeah, it doesn't look like a Z.
Doesn't matter, guys.
He's drawing on
I'm going to have to start recording a different class because you guys pick on me too much. P in the first triangle. is between the unknown and the bigger. So what letter is like that in the second triangle?
Hey.
L is between the unknown and the bigger in the second triangle. L in the first triangle is between the unknown and the smaller. So in the second triangle, what is by the unknown and the smaller? A. Which means that N should match with N, which is good because those are the angles that we know do in fact match up. Questions? Other than the inability to read my handwriting.
Wait, that's it.
What do you say?
All right, one more example. One of these days, I'm going to give one of you the iPad, and then I'm just going to sit here and make fun of your handwriting.
Let TJ do it.
Let Troy do it.
I won't even be able to like draw on the thing.
Is this supposed
The
to
thing would be so big, like,
No, you zoom in and then.
All right. This picture actually illustrates something that happened on your last test, but a lot of you really struggled with the idea of we weren't given how big the sides were, but rather we were given how big the angles were, and then you were asked to put all of the sides in order. And a lot of students really struggle with the idea of that middle one that's in both. How can it be the biggest in one triangle but the smallest in the other triangle? And that's actually what happens here. That 24 is the biggest in the left-hand triangle but the smallest in the right-hand triangle. Okay? One of the struggles with that picture on the test is that it was drawn very, very proportionately, that it really looks like it should have been the same in both of them. But here, once we kind of stretch it out a little bit more, we can see how it would turn out to be the biggest in one but the smallest in the other. Alright, so now for this type of problem here, if we are going to say these are similar, which theorem would we apply? Side, side, side. So now we need to match up and see if our sides do actually turn out to be in the same proportion. So in the left hand, what is the small side?
6.
In the right one, what is the small side? In the left one, what's the medium?
20.
In the right one, what's the medium?
30.
In the left one, what's the big?
24.
And in the right one, what's the big?
36.
So we need to see if they reduce to the same thing. 16 and 24 both reduce by 8 to give 2/3. 20 and 30 reduced by 10 to give 2/3. 24 and 36 reduced by 12 to give 2/3. So it works. We have a scale factor of 2/3. So now we need to name our triangles. I'm going to call the right-hand one ABC. A in the right-hand triangle is between 30 and 24, which is the small and the medium. So in the left-hand triangle, what is between small and medium?
D.
D. B is between the medium and the large. In the left hand, what is between medium and large?
A.
Which means then C must be the other one and C must match with C. Questions? Your homework tonight comes from 7.5, and I'm not sure you deserve this after how much you were picking on me, but you can take off 12 and 13, which are proofs.
But they were easy.